Hello friends, welcome back to my YouTube channel. Today I will continue my discussion on liquid extraction. This would be part number 16 of that discussion, and I will continue my discussion on stage-wise liquid extraction with insoluble liquids. And today I will be discussing a numerical that is based on multistage cross-current liquid extraction. In my previous video, I had discussed the theoretical aspects of three-stage cross-current liquid extraction with insoluble liquids. What are these insoluble liquids? Let me tell you briefly. So, in the ternary system of three liquids, A, B, and C, the feed solution is A plus C, where C is the solute to be extracted and B is the extracting solvent. And then by insoluble liquids, I mean A and B. These are not at all soluble in each other. They are not at all soluble in each other. They are not at all soluble in each other. So for such a system, in my previous video, since part number 12, I have been discussing such a system. In my previous video, I had discussed the theoretical aspect of three-stage cross-current liquid extraction. And based on that, in this video lecture, I'll be discussing one numerical where you'll learn how to find out percentage extraction in a cross-current operation, multi-stage cross-current liquid extraction operation. So let us start the discussion. At first, let us look at the numerical statement. Nicotine is to be extracted from its solution with water. The solution is containing 1% weight of nicotine. The extraction is carried out at 20 degrees Celsius using kerosene as the extracting solvent. The quantity of feed is 150 kg and it is extracted 3 times using 70 kg of solvent each time. Find the percentage extraction for this extraction task. So in this case, we have a feed solution. Feed solution is solution of nicotine in water. The solution is containing 1%. The feed solution is containing 1% weight of nicotine, and this is to be extracted by using kerosene as the extracting solvent. The quantity of feed to be handled, it is 150 kg, and it is extracted 3 times. That means it is to be extracted in 3 cross-current stages using 70 kg of solvent in each stage. So the meaning of this thing is we have to use a 3-stage cross-current operation, and in each stage the quantity of solvent that is used, it is 70 kg. So under these circumstances, we are supposed to find out the percentage extraction in this extraction task. What else is given to us? We have been provided with the equilibrium data. The equilibrium data has various values of these quantities, kg nicotine per kg water. There are different values for this quantity and corresponding values for the quantity kg nicotine per kg kerosene. They are also given to this. The corresponding values in this table, they are in equilibrium with each other. So this values of kg nicotine per kg water and kg nicotine per kg kerosene, which are in equilibrium with each other, they are given to us. And we are going to use this equilibrium data to find out the percentage extraction. So let us start the solution. Okay, first let us list the data that is given to us. you have the feed solution. It is a solution of nicotine and water. In this case, nicotine is C, the solute to be extracted, and water is A, the carrier solvent. And the quantity of feed is given to us. It is 150 kg. That is, F is 150 kg. Then this feed solution is containing 1% weight of nicotine in it. That means you can get weight fraction of nicotine in the feed by dividing the percentage value with 100. So therefore XF will be equal to 1 upon 100. That is 0.01. Then the operation to be used is 3-stage cross-current liquid extraction, because they have told us that the feed solution is extracted thrice. So it corresponds to a 3-stage cross-current liquid extraction operation. The solvent to be used in this case is pure kerosene. It is pure fresh solvent, pure fresh kerosene, not the recovered one. Therefore, there will be no solute in it. That is weight fraction of solute in the solvent, which we denote by YS. It is 0. Then quantity of solvent used in each stage, it is given to us. So S10 it is 70 kg, S20 it is 70 kg, S30 it is 70 kg. That is, in each of the stage, same quantity of solvent is used. But this could be different. Quantities of solvent used in stages, they could be different. In this case, the same quantity of solvent is used in each stage. Then they have given us the equilibrium data. What is this? You have values of kg nicotine per kg water and kg nicotine per kg kerosene that are in equilibrium with each other. These values are given to us. Values of kg nicotine per kg water and kg nicotine per kg kerosene that are in equilibrium with each other, they are given. Now, if you look at this term, kg nicotine per kg water, this is nothing but solute, the amount of solute per kg of carrier solvent. That is, this is nothing but weight fraction of nicotine on a nicotine-free basis in the raffinate. Weight fraction of nicotine on nicotine-free basis in the raffinate. This is weight fraction of solute on a solute-free basis in the raffinate. I have discussed these concentrations in my earlier videos on the topic. I have given link to the playlist which has all my videos on liquid extraction. You please watch those videos. And we denote this quantity, weight fraction of nicotine on nicotine-free basis in the raffinate. We denote it by capital X. Then the other quantity that is given, it is kg nicotine per kg kerosene. That is, it is weight fraction of nicotine on nicotine-free basis in the extract phase. This is weight fraction of nicotine on nicotine-free basis in the extract phase, and we denote this quantity by capital Y. In other words, values of X and Y, weight fractions of nicotine on nicotine-free basis in raffinate and extract phases that are in equilibrium with each other, they are given to us. The values are directly given to us, and we will be using these values to plot the graph. What are we supposed to find? We have to find percentage extraction of nicotine in a 3-stage cross-current operation. So this is the given data. We will use this data to find the percentage extraction that is obtained in a 3-stage cross-current operation. Okay, now let us solve the numerical. First, we will do calculations for first stage. First, we will calculate capital XF. How do you calculate capital XF? Capital XF is small xf divided by 1 minus small xf. Small xf is given to us, it is 0.01. So if we use this value, you will get capital XF is equal to 0.01 divided by 1 minus 0.01. That is, XF comes out to be 0.0101. Then we have to calculate capital Ys. How do you calculate that? Capital Ys is equal to small ys divided by 1 minus small ys. But small ys is 0 since pure fresh solvent is used. Therefore, capital Ys will be equal to 0 upon 1 minus 0, which gives capital Ys as 0. Capital Ys is also 0. Then we have to calculate the amount of A in the feed. Calculation of the quantity of A. So how do you calculate it? Since weight fraction of solute in the feed is XF, so weight fraction of A in it would be 1 minus XR because feed is containing A and C in it. And for C, the weight fraction is XF. So weight fraction of A will be 1 minus XF. And in order to get the quantity of A in the feed, we'll have to multiply with its weight fraction. Multiply the quantity of feed with its weight fraction. And that is what I have done in this equation. So amount of A is equal to amount of feed into 1 minus XR. F is 150 kg, that is given to us. XF is 0.01. Again, this is given to us. So therefore, A will be equal to 150 into 1 minus 0.01. That gives us A as 148.5 kg. Then we have to calculate quantity of B1. That is amount of solvent that is admitted to stage 1 or that is used in stage 1. So quantity of B in that solvent, it will be B1. 1 stands for the stage in which it is used, first stage, so B1. So again it is clear, B1 will be equal to S10 into 1 minus Ys, because Ys is weight fraction of the solvent will be containing B and C in it, and weight fraction of C is Ys. So obviously, since there are only two components, weight fraction of B will be 1 minus Ys. But in this case, Ys is 0. So therefore, S10 is 70 kg and Ys is 0. Therefore, B1 will be equal to 70 into 1 minus 0. That gives us B1 as 70 kg. So after getting quantity of A and quantity of B1, we will find slope of the operating line for stage 1. So slope is given as minus K upon B1. That is, slope will be equal to minus. So if you put the values, A is known to us. A is how much we got? It is 148.5 divided by 70. So slope is minus 148.5 divided by 70. And this is minus 2.12. The slope, therefore, the slope of the operating line for first stage is minus 2.12. Therefore, the angle made, that is tan theta, is equal to minus 2.12. So therefore, theta will be equal to tan inverse of minus 2.1t, and this is nothing but minus 64.65 degree. So the angle made by the operating line with the horizontal, you have to measure it in a clockwise direction. So you'll be measuring it like this, and the angle in this case is 64.65 degree. The negative sign indicates that you have to measure it in the clockwise direction. So this would be the operating line in this case. Okay. So at the end of these calculations, we have got the slope of the operating line for stage 1, and we will be using it to plot the operating line on the equilibrium diagram. So let us do that. So let us plot the graph. So on the x-axis, we are going to plot capital X. On the y-axis, we are going to plot capital Y. So if the given data is plotted, you are going to get the equilibrium curve. Okay, so for first stage, the operating line for first stage, endpoints of the operating line, one endpoint is XFYS and the other endpoint is X1Y. These endpoint you can locate it because XF and YS, they are known, and we have to find out the other endpoint, coordinates of the other endpoint, that is X1 and YY. Slope we just got, that is minus 2.12, or angle measured in clockwise direction is 64.5 degree. Now first let us locate the point whose coordinates are known to us, XF and YS. So XF is, capital XF is 0.0101, we have just calculated it. Capital YS is 0. That means this point XFYS, it will be located on the y-axis at x is equal to XF. So it will be located over here. This is XF and the operating line will start at this point. Now the task is to plot the operating line which has a slope of minus 2.12, or the line which makes an angle of 64.5 degrees, which is measured in a clockwise direction. Now I have in my previous video, or in my video in which I had discussed numerical on single stage extraction, I have told you how to plot the operating line, the desired slope. So let me tell you again. So here one thing is you can make the use of the angle. So you have to plot a line which makes an angle of 64.5 degree. In this way, the line is having negative slope, or we can make use of the definition of tan theta. So if I show the line, so this theta is known to us. Let me call it as theta, and this is the right angle triangle. So in this right angle triangle, tan theta is, let this side be M and let this side be N. So tan theta will be equal to M upon EL. And if I make N equal to 1, then in that case tan theta will be equal to M. That is, the slope is equal to M. So I will use this approach to plot the operating line. So what I will do, I will start at this point. I will have to travel a distance. Let me tell you, you can use this approach only when the scale on both the axes is same. So you can check on x-axis scale is 1 centimeter is equal to 0.005, and I have the same scale on the y-axis. So if you can use this approach if you are using the same scale on both the axes. So as per this approach, I will travel 1 unit to the left of this point. Why to the left? Because I have to plot a line of negative slope. So if I travel 1 unit, I will reach over here, and then in the vertical direction, I will have to travel a distance that is equal to the slope, and slope in this case is 2.12. So if I travel this vertical distance, so it will be 1, 2 and 2.1. So I reach over here. Okay, so I get this point, I have this point. Now the task left is to draw a line that passes through this and this point. So that will be the line of the desired slope of minus 2.12. So after plotting the line, next is I will have to, the line will be intersecting with the equilibrium curve, because we are considering the stage to be ideal. All the stages are considered to be ideal, so that the leaving phases, they will be in equilibrium with each other. So I am interested in finding out the coordinates of the point where the operating line intersects the Euclidean curve. So the x coordinate of this point will give me x1, and the y coordinate of this point will give me y. So if I read these values, x1 and y1, x1 in this case, it is 0.0071. So you can 0.005, 0.006, 0.007, and the point is located at 0.071. Whereas y1, it is 0.0065, 0.005, 0.006, and 0.065. So this is my calculations for stage 1. So at the end of these calculations, I have got values of x1 and y1. Okay, now let us move on to the calculations for second stage. Okay, now let us start our calculations for the second stage. From our calculations for stage 1, we have got value for capital X1, 0.0071. Then we have got value for capital Y1, that is 0.0065. And A, we got it previously. Quantity of A, it is 148.5 kg. Now, for second stage, let us calculate Ys, because the solvent that is used in second stage, it has composition of Ys. So capital Ys is small ys divided by 1 minus small ys. Very simple calculation. Ys is 0. Therefore, capital Ys, which is 0 upon 1 and a 0, capital Ys will also be equal to 0. Then we have to calculate quantity of Beta. In for first stage, we calculated quantity of B1. Now for second stage, let us calculate quantity of Beta. Therefore, B2 will be equal to S20 into 1 minus Ys. I have told you how we get the equation. Therefore, in this case, S20 is 70 kg, Ys is 0. Therefore, B2 will be equal to 70 into 1 minus 0. That is, B2 comes out to be 70 kg. Then we have to get the slope of the operating line for stage 2. So slope is minus A upon B2. And if you use the values, so that is equal to minus 148.5 divided by 70. And this comes out to be minus 2.12. Slope, therefore, slope of the operating line for second stage is again minus 2.12. Okay, so once the slope is known to you, then let us plot the operating line on the graph. The graph that was previously drawn, I am taking that graph in my discussion. Now, for the second stage, the operating line for the second stage, the operating line has endpoints. These endpoints, which are this capital X1 Ys and X2 Ys, X2 Y2. Out of this, the first endpoint is known to us. Endpoint with coordinates capital X1, capital Ys, that is known to us. So, X1 is over here. Operating line for the second stage, it should start at this point. And slope of the operating line is minus 2.12. That is the angle made by the line. If it is measured in clockwise direction, that is minus 64.5. So the line will be making an angle of 64.5. So again, I will use the approach that I used previously for plotting this operating line. Or else, since the slope is same, slope of the operating line for first stage and then for the second stage it is same, you can just draw a line that is parallel to the operating line for first stage, parallel to this one. You can do that, or you can use the approach where a definition of tan theta is used. So I'll use that. So my aim is to get start the operating line at this point. So I will travel a distance of, okay, before that we need to locate the point x1 ys. X1 is 0.0071 and ys is 0. So this point will be located over here, where the x coordinate is equal to x1, and now the operating line should be drawn from this point. So if the approach of definition of tan theta 1 is used, or tan theta is used, so I'll have to travel 1 unit distance to the left of the point. So I'll arrive at this point, and then I will have to travel a distance equal to the slope in the vertical direction. So if I do that, I arrive at this point. So the operating line for second stage will be drawn through this point and this point. And that will be the operating line for second stage. And then I'm interested in finding out the intersection of this operating line with the equilibrium curve. Here is the intersection, because the coordinates of this intersection point will give me x2 and y2. So this will give me x2, and the y coordinate, it will give me y2. And if you read the values, you can note the values of x2 and y2. So x2 in this case is 0.005, you can check, and y2 in this case is 0.0045. So at the end of our calculations for stage number 2, we have got the values for x2 and y2. Now let us proceed to calculations for stage number 3. Okay, so let us proceed for calculations for third stage. So from our calculations for stage number 2, we have got capital X2 as 0.005 and capital Y2 as 0.0045. A is 148.5 kg. Then we need to calculate capital Ys. Actually, we have already calculated it, but in order to follow the steps, I am showing these calculations. Capital Ys is ys, small ys divided by 1 minus small ys. Ys is 0 for this stage also. So therefore capital Ys will be equal to 0 upon 1 minus 0. That is capital Ys is equal to 0. Then calculation of quantity of B3. Amount of B that enters stage number 3. So this will be B3 will be equal to S30 into 1 minus Ys. I have told you how we get this equation. S30 is 70 kg, Ys is 0, therefore B3 will be equal to 70 into 1 minus 0, that is B3 will be equal to 70 kg. Now let us calculate the slope of the operating line for stage 3. So the slope is minus A upon B3, that is minus 148.5 divided by 70, that gives a slope, again it is minus 2.12, same slope. Slope for every line, operating line is same. That means the angle in this case is minus 64.5 degree. So the line will be making an angle of 64.5 degree. Okay, now next we will be plotting the line. We will be plotting this line. So now let us look at the graph. We will take our previous graph into our discussion. So far we have plotted operating line for the first 2 stages. Now let us plot the operating line for the third stage. So endpoints for the operating line or third stage. One endpoint is x2, capital X2 Ys, this is known to us. The other endpoint is x3, y3. We are going to get these values at the end of our calculations for this stage. Slope is minus 2.12. So that is theta is minus 64.5 degree. Okay. And first we will have to locate the point x2 ys. So the point is over here. x2 and ys is 0. That means the operating line for the third stage, it will start at this point. And I will use the approach of using the definition of tan theta. So I will have to travel 1 unit. Okay, x2 is capital X2 is 0.005 over here. Ys is 0. So the operating line is going to start at this point. And in order to plot the line of the slope, desired slope, I will travel 1 unit to the left in a horizontal direction, and then a distance equal to the slope in the vertical direction. I get this point. So the operating line for this third stage, it will pass through this point and this point. So this will be the operating line. And now let us look at the intersection of this operating line with the equilibrium curve, because that the coordinates of this intersection point are nothing but x3 and y3. So x coordinate is over here, it is x3, and y coordinate is over here, it is y3. So if you have to know the values of x3 and y3, let us write those values. x3 is over here, which is nothing but 0.0036. So 0.001, 0.002, 0.003, and 0.0036. Whereas y3, it is 0.003, 0.001, 0.002, and 0.003. So at the end of our calculations for stage 3, we have got the values of x3 and y3. So this covers all the 3 stages that are used in this operation. Now let us go to finding the extraction, percentage extraction. Okay, so percentage extraction, let us calculate percentage extraction. For the first stage, we got x1, capital X1 as 0.0071, capital Y1 as 0.0065. Now, let us find out the quantity of nicotine that is extracted in stage number 1. And I am going to denote that as CE1, amount of nicotine extracted in stage 1. So for that, we are going to use the value of Y, capital Y. Capital Y1 is 0.0065. What is this? This is kg nicotine per kg kerosene in stage 1. That means if I multiply this quantity Y1 with kg kerosene amount of quantity of solvent in stage 1, which is B1, I will get kg nicotine that is present in the extract phase. This is kg nicotine per kg kerosene in the extract phase. And we know the quantity of kerosene, that is B1, quantity of B1 is known to us. So you can easily get kg of nicotine in the extract phase. So it will be CE1, that is extracted, kg of nicotine extracted, CE1 in the first stage is equal to Y1 into B1, because it is per kg, and if I per kg kerosene, and if I multiply with kg of kerosene, I will get kg of nicotine. So CE1 will be equal to capital Y1 into B1. B1 is 70 kg. So it will be CE1 is equal to 0.0065 into 70. So that gives CE1 as 0.455 kg. That is the kg of nicotine that is present in the extract phase obtained out of first stage is 0.455 kg. Now let us do it for the second stage. For second stage, we got capital X2 as 0.005 and capital Y2 as 0.0045. And again, we will get extracted nicotine. The amount of nicotine that is extracted in second stage, I will denote that quantity as CE2. So for that, we will be using the value of Y2, which is 0.0045 kg nicotine per kg kerosene in the extract that is obtained from stage 2. That means if I multiply Y2 with B2, I will be getting kg nicotine that is present in the extract phase that is obtained in stage 2. So therefore Ce2, that is kg nicotine, quantity of nicotine in the extract of second stage, it will be capital Y2 into B2, and B2, let me erase this, B2 is 70 kg, therefore Ce2 will be equal to 0.0045 into 70 because Y2 is 0.0045. That gives me Ce2 as 0.315 kg. That is amount of nicotine obtained in the extract from second stage is 0.315 kg. Now let us do the calculations for third stage. For third stage, we obtain capital X3 as 0.0036, capital Y3 as 0.003. Now the extracted nicotine in the third stage, let us denote the quantity by Ce3. So Ce3, in this case, for getting Ce3, we will be using the value of Y3, which is 0.003 kg nicotine per kg kerosene, that is B3 in the extract that is obtained in the third stage. So if I multiply Y3 with B3, I will be getting kg nicotine in the extract that is obtained from the third stage. So Ce3 is equal to Y3 into B3. That is B3 is 70 kg, therefore Ce3 will be equal to 0.003 Y3 into 70. That gives me Ce3 as 0.21 kg. In this way, we have got the amount of nicotine that is extracted in each of the stage. In the first stage, it is 0.455 kg. In the second stage, it is 0.315 kg. And in the third stage, it is 0.21 kg. Now, the addition of all these three quantities will give us the total quantity, total amount of nicotine that is extracted. And we are going to use that quantity to find out percentage extraction. So let us do that. So percentage extraction. Now the total nicotine extracted, I'll denote it as C. This will be addition of nicotine that is obtained in all the three stages. So Ce will be equal to Ce1 plus Ce2 plus Ce3. Ce1 we got 0.455 kg. Ce2 we got 0.315 kg. Ce3 we got 0.21 kg. Therefore Ce will be equal to 0.455 plus 0.315 plus 0.21. That gives Ce as 0.98 kg. That means the total amount of nicotine that is extracted, it is 0.98 kg. Now let us find out percentage extraction of nicotine. So percentage extraction will be Ce, that is total amount of nicotine that is extracted divided by CF. What is CF? Amount of nicotine in the feed. Here CF is nicotine in the feed, quantity of nicotine in the feed. And how do you get it? You know the weight fraction, you know the total feed. Therefore, quantity of nicotine in the feed, that is CF, will be equal to XF into F. And therefore, if you use this to get the percentage extraction, it will be percentage extraction will be equal to C upon XF into F into 100. Therefore, percentage extraction will be C is 0.98, XF is 0.01 and F is 150. So, percentage extraction will be 0.98 divided by 0.01 into 150 into 100, and that gives percentage extraction as 0.98 divided by 1.5 into 100. Therefore, percentage extraction comes out to be 65.33. Therefore, percentage extraction of nicotine that is obtained in this three-stage cross-current operation is 65.33. So with this, I end my discussion for this numerical. At the end of this numerical, we have got percentage extraction in a three-stage cross-current operation. I hope you have learned how to get the extraction, a percentage extraction. If you have any doubt, you please mention that in the comment section. let me end this discussion for this video. And in my next video, I will be discussing multi-stage counter current liquid extraction. So thanks for watching this video. Do subscribe to my channel. Tell your friends to subscribe to it. And do hit the like button if you like my videos. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. For now, thank you. Have a nice day and hope to see you soon in my next video.